Good morning, everyone. Thank you for joining us today. My name is Lynn Dobbin. I am the Managing Director for Purdue's Institute for a Sustainable Future, and we are happy to once again partner with our friends at White River Alliance and then have some speakers from another partner, Hoosier Environmental Council, and to discuss today's topic on coal ash risks, remediation, and recovery. Just a few housekeeping things. We do have a Q&A tab available for people to ask questions, and our panelists will try to look through those and address them, as well as have a general discussion and answering of questions at the end of our presentations. We will be having three speakers. There will be a short opportunity to ask questions at the end of each one. The recording for this will be available at our Institute for a Sustainable Future YouTube site. And so once it is recorded and uploaded, I will send out an email to everyone who is registered so that they are available to see it and share it with others. Without further ado, I am going to go ahead and hand over the microphone to my colleague Jill Hoffman from the White River Alliance, and she will go through the agenda and introductions of our panelists.
Great. Thanks so much, Lynn. It's nice to see you again doing these fun science and policy forums that we do together. I really appreciate it.
It's great.
Working on a screen share here. If you can just give me a second, I'm going to give you guys an idea of where we're headed today with our program and do a little introduction of our amazing speakers that we have for you today. So as Lynn mentioned, she just started things off for us, and we are really grateful to partner with Purdue on these science and policy forums. These sorts of forums are an extension for us of our work organizing the Indiana Water Summit. And so many times there are topics that we want to take on at the summit, and they're simply maybe too complex to fit into a 45-minute talk. And this is one of them as this issue continues to plague our water supply. So proud to be here with this team of amazing presenters. We have Professor Grace Schwartz joining us as our first speaker today. And as you can see there, oops, sorry about that, hop forward. As you can see there, Grace is an assistant professor at Woodford College in South Carolina. And all of her esteemed credentials are listed there for you, along with other lots of publications that she has been part of, including the environmental impacts of combustion residuals and understanding the different risks and perspectives. So we're grateful she will be here to share all of her research and knowledge on that. Following Grace, Dr. Indra Frankwell, who is as Lynn mentioned, a longtime partner of both of our organizations. We're glad to have Indra back with us. And Indra has an MD from Johns Hopkins University, the School of Medicine, and a master's from of public and environmental health from Indiana University. So she has been working on these issues for quite a long time, and fierce advocate in Indiana's history here at the State House, including issues of coal ash. So we think she retired. It seemed like she retired from working with Hoosier Environmental Council, but she stays in this role on coal ash as it is a topic near and dear to her heart. We appreciate you coming back to join us, Indra. You probably are always my go-to expert on this topic, no matter where you live or no matter if you're retired. Okay, and then Dr. Maria. Oh, this is a good one. Mastoleritz. No, I have no idea. How did I do? Maria, you can clean that up for us later.
Anyway. Yes. You're pretty good.
Okay,
pretty good,
perfect. Yes. Thank you so much. Sorry for that. Okay, I should have practiced in advance. And Maria is a senior scientist at the Indiana Geological and Water Survey, IGWS, received her PhD, as you can see there, in Poland, which is amazing. So we will enjoy both your knowledge and your accent as we learn from you today. We work with IGWS on a number of things, including most recently exploring the monitoring network. So we appreciate what you guys are doing there as well. So you have published over 300 research papers. This is amazing on coal geology. So in the Journal of Coal Geology. So looking forward to learning from you as well. So I think with that, I'm going to stop my screen share, turn things over to the real experts in the room, and then just thank all of our participants for being here. As I work on water issues, I'm always amazed at the complexity of things that impact our environment, and this is certainly one of those that has lots of facets, risks, recovery, lots of things going on. I just saw a news article this morning in the Capital Chronicle where you were mentioned, Maria. So we are timely on this topic and appreciate you all being here. With that, I think I'm going to turn it over to Grace if
Okay.
she's ready. Grace, are you ready
Yes.
for us?
Let
Okay.
me share and put this into presentation view. Okay, can everyone see that?
Yeah,
Okay.
looks great.
All right, so my job today is to kind of set the stage and give some of the scientific background on what coal combustion residuals or coal ash is and some of the environmental impacts we've seen from, I would say, improper disposal of these materials. So coal ash or coal combustion residuals are made up of three main components. So we have bottom ash, which is collected from the bottom of the furnace at your coal-fired power plant. So bottom ash materials are heavier materials. So they're things that are going to sink to the bottom of that furnace, and they can be kind of gravel size, pebble size, and they tend to be enriched in elements that are not as volatile. So elements that when you heat them really hot in that furnace, they don't go into the gas phase as easily there. The second main component of coal combustion residuals is fly ash. So fly ash is composed of the really fine particulate matter or ash particles that are so fine and so light particles that they can remain suspended in the gas stream at the coal-fired power plant. So you're kind of moving from the furnace into the depths of the plant here. And fly ash tends to be enriched in trace elements that are a little bit more volatile. So in the furnace, things get heated up really hot and you tend to move a lot of your chemical elements into the gas phase. And then as you follow along the power plant and move further away from the furnace, things start to cool down a little bit and you start to have more of those elements condensed onto the particles that are suspended in your gas stream. And fly ash is collected these days through a series of air pollution control devices that you would have on your power plant. So that will vary by power plant, but it's kind of collected in the middle of your plant. And then as you move along, getting closer and closer to the end of your power plant to, your final air pollution control devices, we have flue gas desulfurization wastes that are taken out. So flue gas desulfurization is an air pollution control device that was designed to take out sulfur dioxide from power plant emissions. So it's done a great job of reducing those air emissions so we don't have acid rain as a problem so much in the US anymore. But those wastes trap your most volatile elements that are coming from coal combustion. And so those include selenium and mercury. So solid waste from flue gas desulfurization tends to be enriched in those elements. So CCRs, in summary, they're a mixture of bottom ash, fly ash, and flue gas desulfurization wastes. And there's so many different chemical elements involved in the waste. So you kind of have a backbone of unburned carbon, iron minerals, aluminosilicate minerals, glass, and then all interspersed in that, absorbed onto that kind of framework and tucked into the crevices there are trace elements. And you can really kind of look at the periodic table and find a lot of things that are in there. And some of the big ones that we worry about are things like arsenic and selenium and mercury that have very big health impacts. So this graph is from the United States Energy Information Administration, and it is showing our electricity generation power sources over the years. So starting at the left edge of the graph, we're seeing 2001 and kind of bringing us up to 2023, so almost present day. And coal is this black patch at the bottom here. And you can see that we kind of reached a peak around 2008 with how much power we were generating based on coal. And since then, we've kind of been in this long decline. And a lot of this is due to the rise in natural gas electricity generation in this country. And then more recently, we see more and more renewables coming into play. But back in 2008, around that time frame, we were generating over 130 million tons of coal ash every year. So that's a lot of solid waste. We aren't generating that much anymore, but coal still makes up a decent portion of our electricity generation. And then you have to think about all those years where coal really was king and we were generating so much ash every year. We still have a lot of legacy coal ash waste to deal with. So where does the CCR waste go once you've generated it at the power plant? So with solid waste, a large amount of it has been reused in different processes. So this has included use as structural fill, use in cement blocks and drywall are some of the main uses for CCRs for beneficial reuse. And then the amount that is not beneficially reused has to be stored somewhere in a long-term disposal. So historically, that was in surface impoundments where the waste was kept as kind of a wet sludge in these big holding ponds. More recently, we're seeing more and more dry landfilling as we learn more and more about the environmental harms of surface impoundments. That's kind of been the big switch in industry to go towards these landfills. But there are a lot of environmental implications around these legacy impoundments that we still have around. And I'm going to talk a little bit about those, but they include kind of groundwater infiltration from leaching of trace elements out of the ash through many of these impoundments are unlined. So there's not a liner on the bottom to keep the trace elements from infiltrating groundwater. There's been discharge from ash impoundments of water into the environment, and also you can have direct discharge of aqueous waste from the CCR process just in the plant as well. And then you also have the risk of ash impoundment failure. So this is kind of the environmental impact that might pop into your head when you think about the dangers of coal ash disposal. Here are some pictures from some of the most unfortunate impoundment failures that we've had in the last couple decades. So the biggest one being the Kingston, Tennessee coal ash failure in 2008. Lake Michigan was another one, Dan River. So these are instances where there was a structural failure of the impoundment resulting in a large leak of coal ash, and it contaminated surface waters, can also lead to groundwater contamination. But probably the biggest source of environmental impact is not these spectacular impoundment failures, but maybe more everyday occurrences. And this would be discharges from the power plant, either directly from the aqueous, all the water that's running through the power plant being discharged, or from discharge from the ash ponds. As that sludge enters the pond, the solid settles to the bottom and you're left with a supernatant water, and some of that has to be discharged over time. So this slide is showing back in 2012, I was in graduate school at Duke, and I was part of a study that looked at surface water contamination around North Carolina from CCRs. So we sampled 10 different lakes around North Carolina. 9 out of the 10 had a power plant on them, so they were receiving impoundment discharge. And I'm just showing a very little snippet of the data. So we have a graph for arsenic here on the left and a graph for selenium. And this is showing the arsenic and selenium levels in the impoundment effluents. So these were samples that were taken directly where these ash ponds were discharging into the lake or the river that we were sampling. And the colors stand for different types of impoundments. So if you see red, this was an impoundment that contained FGD waste, or those flue gas desulfurization wastes. If it's blue, it was mainly a fly ash impoundment. Black, cooling water, so not as impacted by the CCRs. And then the green was a control lake. But I just wanted to highlight that there were a couple lakes that definitely had higher concentrations of arsenic and selenium that were being discharged out of the power plants. And some of the levels were quite high above the EPA kind of guideline limits. Groundwater contamination is another environmental impact to worry about. So I'm highlighting North Carolina again because that's where I went to graduate school. So I'm most aware of the concerns in that state. So in 2013, the North Carolina State Environmental Agency found groundwater exceedances at all 14 Duke Energy power plants, coal-fired power plants across the state. And this was for many different elements. So that's definitely a concern, especially for communities that live near these plants and are exposed long term to these contaminants in the groundwater. So thinking about all these kind of environmental concerns surrounding CCR materials, you might be wondering, well, why did we decide it was okay to put them in these big impoundments in the first place? And there's a lot of history behind that around the policy making, and I know Indra's going to talk more about the policies, so I'll let her get into that. I'll stick more to the sciencey side here. One of the reasons has been the tests that we use to determine whether a material should be considered a hazardous waste or not. So historically, the main test has been the EPA's toxicity characteristic leaching protocol, or TCLIP. So this test was designed mainly with municipal landfills in mind and thinking about what waste should go in there or what should be segregated. And with this test, you would mix up your solid waste material with a kind of mildly acidic solution for 18 hours, and then you measure what is leached out. And there's a threshold, you compare to see if you meet the limit or not. And it turns out when you apply this test to coal combustion residuals, most of them will pass it. And so they would not be considered hazardous waste. The problem is that the conditions captured by these tests are not the conditions that are encountered by CCRs out in those impoundments, or if you have an ash spill, the conditions that the ash is going to encounter, once it's escaped into the environment. So out in the real world, we are encountering variations in oxygen concentration. So you might have ash hitting anoxic zones where there's very little or no oxygen. You have the presence of other chemistry like dissolved organic matter that can impact how easily these elements leach off of the coal ash. And then there are also microbial activities that kind of get into this complex interplay with the oxygen levels that affect leaching as well. So arsenic and selenium particularly are very sensitive to oxygen levels, and that affects how well they leach in the environment. So these are all factors that really aren't captured at all in the TCLIP test. And, as we've learned more about the environmental harms of coal ash and improper disposal, the EPA has been well aware of this. And they developed a new leaching protocol, the Leaching Assessment Environmental Framework. So these are a series of tests. I believe it's 4 or 5 different tests that try to get at the complexity a little bit more of leaching from a material like coal ash. So they look at a broader pH range. They look at different solid to water ratios and things like that. So it's a big improvement. But unfortunately, those tests still don't capture things like oxygen variation, having dissolved organic matter around. So we're still not quite there with capturing the complexity. So a lot of my PhD work was around trying to figure out if we could predict leaching potential of these elements like arsenic and selenium from the coal ash. And so the goal for me was to figure out if there was something about the coal ash that I could measure before it hits water that would give me some indication of whether this is going to be a bad one or not, how careful we'd have to be with disposal. And what I really found through my work is, yes, you can kind of look at the trace element content and see, if you have an ash that has tons of arsenic in it, that probably is one that you should be wary of. But really looking at those elements alone and just how much is present in the ash is not a great predictor of how much will leach once it hits the environment. So you really do have to kind of combine a characterization of your ash up front with these key environmental parameters that it might encounter in the disposal situation. And that just makes predicting leaching potential really hard and difficult because every impoundment you can imagine is going to be a little bit different. Those environmental conditions that it might encounter are hard to predict, and especially if you don't have any data about what your impoundment is like at that particular power plant. And that makes it hard to come up with a test that can be applied, across the country to say everyone do it this way to predict how well your elements will leach from the ash. So that's really something that I think we're still struggling with is how to predict, how well that ash is going to hold up in the environment and how it should be stored. I wanted to touch briefly on beneficial reuse because that has been um, a big factor in developing policy around coal ash disposal, and it's also a huge industry. So traditionally, there have been two pathways for beneficial reuse. So you can kind of roughly divide things into encapsulated reuses and unencapsulated reuse. So with encapsulated reuse, we're thinking about reuses where the ash is very contained, so kind of locked up in a structure. So if you make ash into a cement block or something like that, or concrete, it's got a lot less exposure to the elements, a lot less potential for leaching. So that in general has been thought to be a pretty safe way to reuse coal ash. I think there are still some concerns around material stability when exposed to kind of extreme conditions. So if you took some of those materials and put them underwater for a very long time, what would that mean for leaching of elements out of those materials? And also the trace element content. So just thinking about the whole periodic table that could be in those materials and, well, what if we have an enrichment in radioactive elements? Or, what if we have a lot of arsenic in that material? Just being careful to know exactly what is in that and thinking about long term how it's going to hold up over the years. The reuse method that we would say probably is not a very good idea would be unencapsulated reuse. So this is thinking about things like spreading fly ash on crops as a fertilizer amendment or a soil amendment, putting it on roadways as de-icing or something like that, using it as a bank fill or structural fill. So, and these methods, you're spreading the ash out, you have a lot of exposure to environmental conditions, and you're really, in effect, making a small ash spill, if you will. So this is really not a great idea when it comes to exposure to trace elements in the environment. And then the last thing, kind of thinking ahead, future challenges and perspectives, we have many of these ash impoundments spread out over the country. We might not be adding to them anymore as much, but we have these legacy impoundments that we're still dealing with the environmental risks associated with them. And we also have a changing climate. And this is a figure from the paper that me and my colleagues published recently in 2023. But we mapped out kind of where all these ash impoundments are, and we're thinking about the natural hazards that could be associated with having the impoundments in these spots. So impoundments that are in floodplains. So this picture shows impoundments that are in the 100-year floodplain in the blue, and impoundments that are in the 500-year floodplain in the red. And as the climate changes, we're getting more and more kind of abrupt extreme rainfall events or hurricanes coming through that are dumping many, many inches of rain. So flooding of these impoundments is becoming a bigger and bigger risk. In my neck of the woods in South Carolina, we just had Hurricane Helene come through last year. And then the Western North Carolina area, some areas got 20 to 30 inches of rain over just a couple days. And so you really worry about structural integrity of these impoundments and, flooding of them and spreading this contamination around. So things to think about in the future of, as we deal with the legacy of these impoundments and thinking about cleaning them up, keeping the changing climate in mind. So that was my brief overview. And I think we were going to have a little bit of a time for questions before we switch to Indra.
Yeah, that's right, Grace. That was a fantastic overview that I really probably wish I would have heard or sat through earlier before I got where I am now and trying to comment on specific cases. But certainly a risk to our water resources going on here. And that map is, I'm sure Indra will touch on how much this impacts Indiana in particular. But how are we doing out there with the audience? Do you guys have some questions for Grace? Just a couple before we take on the next piece of this puzzle? Lynn, I assume you're watching.
Yeah, it looks like
chat as
Scott
well.
had his, Scott had his, hi Scott, he got his answer.
Okay,
So
I
there
see
was
that.
none other in Q&A.
Okay,
So I think at this point we're okay to move on to Indra's presentation.
great. Thanks, Lynn. Indra, welcome back.
All right. So Grace, if you could stop sharing your screen, I'll go ahead and put my slides up. All right. And Jill, are these showing up all right?
Yes, dear. We need you to get in presenter mode. Yep, that's perfect. That
All
looks
right,
great.
terrific. Oh, well, Grace has certainly set the stage in an excellent manner on what is coal ash and what can it do as far as contaminating water. My job is to talk about policy, meaning what laws, rules, or regulations are there regarding coal ash disposal. And because it's an environmental hazard, as Grace carefully spelled out, that's why we actually need policy on this. But I'd like to start with a little bit of Indiana context to add to what we've already seen. This is a map of coal ash sites around Indiana. Each of the orange triangles is a site where we have a large quantity of coal ash stored. These are all sites where there is currently a coal-fired power plant or where there has been a coal-fired power plant in the past. And what you'll notice as you look at the map is that these sites are all either next to Lake Michigan or next to one of Indiana's major rivers. That's because our coal-fired power plants needed ready access to cooling water. And then as they disposed of their coal ash, they tended to do what was least expensive, which means they disposed of it right next to the power plant. And that means the majority of our coal ash is also right next to either Lake Michigan or one of our major rivers. So where we have coal ash is an important context as we think about what kind of policy we might need. Also, how much is a big question. Indiana is still producing approximately 5 million tons per year of coal ash. The amount being produced was dropping during the early 2000s and the 2010s, but as of about 2020, the amount produced per year has stabilized, and we've even seen something of a rise. because some of the coal-fired power plants in Indiana that were scheduled to close are actually continuing to burn coal now and delaying their closure, largely because of the data centers that are being built and that need such huge amounts of electricity. So we have a legacy from burning coal for many decades. Indiana started burning coal for electricity about 100 years ago. So we have many decades built up. I would say we've got at least 100 million tons stored around the state, and then we're adding 5 million tons per year. And there are problems with coal ash, and these are problems that have to be addressed if we're going to have policy regarding coal ash disposal. First off, that it contaminates water, as Grace carefully illustrated for us. So anytime coal ash gets wet, it contaminates the water. A permanent disposal solution for coal ash has to keep the coal ash dry. Second, if coal ash is dry but open to the air, it can become a dust hazard. Coal ash has very fine particles in it that are extremely hazardous to inhale. And then finally, if an impoundment or a disposal structure isn't strong enough, we can wind up with spills of the coal ash that contaminate soil and have a smothering effect on waterways. And I would actually add one more to this list, one more problem with coal ash that needs to be addressed with policy, and that's the fact that coal ash is a waste that doesn't break down over time. There are many types of waste that chemically degrade or undergo biodegradation over time. Coal ash is not one of those. The contaminants in coal ash are minerals and metals. So when we look to policy to find solutions for coal ash, we need to find permanent disposal solutions. Also, as we head into talking about what policies exist, I think it's helpful to have a perspective on what was happening to coal ash before there was any policy. As I mentioned, Indiana has been burning coal for about 100 years for electricity. And for the majority of that time, there were no regulations or policies regarding coal ash disposal. It was left to the utilities to decide what to do with the waste material. And of course, our utilities were also under a lot of pressure to keep electricity rates as low as possible. So they tended to do what was least expensive. And what was least expensive was to dispose of it near the power plant and without adding a lot of infrastructure like a liner under the coal ash. So this photograph helps illustrate what has happened at the majority of Indiana's coal ash sites. And first, let me kind of talk you through the photo. Here in the upper left corner, we have one of Indiana's major rivers flowing by. To the right of that river in the upper right, of course, we've got the power plant with its 2 smokestacks. And just to the right of that, you can see some itty bitty dots. There's about 5 itty bitty dots to the right of the power plant. I'm showing those for perspective. Those are vehicles parked in the parking lot. So that gives you some notion of the scale of what we're looking at. The coal ash ponds are these sort of polygons of greenish to grayish material. These are open coal ash impoundments or coal ash ponds. At this location, the ponds occupy more than 80 acres, and they're surrounded by berms that are made up of a mixture of soil and coal ash that hold the coal ash in place. These structures were built without liners. One of them had a partial liner under it, but it wasn't a liner that meets current standards. And this is an illustration of what's happened at most coal ash locations around Indiana. We have disposal in the floodplain of a major river, and its disposal in unlined pits that are contaminating the groundwater. Indiana only has one coal ash location that I know of where there was enough natural clay under the coal ash that the impoundments did not contaminate groundwater. So prior to regulation, what we wound up with was the majority of our coal ash in the floodplain in unlined disposal structures and contaminating the groundwater. So that's kind of the setting that we we have as we go into a period where we've started to have some regulation. In 2015, the EPA implemented the first federal coal ash rule. It's also known as the CCR rule. As Grace pointed out, CCR is coal combustion residuals, which is the other name for coal ash. This federal rule had some important provisions in it. First off, it had provisions regarding where disposal units are allowed. For example, you're not allowed to build a new coal ash disposal unit in an area where there's seismic activity and a risk of an earthquake, or in an area where the aquifer is very shallow, and so you're at risk of contact between the coal ash and the groundwater. There are also provisions on how coal ash disposal structures are built, how they're structured, and requirements regarding groundwater. So this is one of the main mechanisms that will get us some coal ash cleanup. All of the disposal sites that are covered under the rule are required to test the surrounding groundwater. And if they show that the groundwater has been contaminated by the coal ash, they're required to take steps to address that contamination. There are also provisions regarding closure. And what closure means is that when they stop putting coal ash into a landfill or into a pond, that pond or landfill has to be closed so that it will endure sort of in perpetuity. Closure generally includes putting an impermeable liner plus layers of soil over the top of either the landfill or the pond. So the federal rule has provisions about closure. It also has provisions about record keeping and transparency. And in this case, in this rule, transparency means that the owners and operators of coal ash disposal units are required to post documents about their coal ash and about all of these other provisions of the rule in a publicly accessible website. The reason that transparency was built into the rule is that this rule was written as self-enforcing. Self-enforcing means that the rule is in place, the utilities are required to comply with it, but the EPA was not taking any steps to oversee implementation of the rule and not taking any steps to enforce it. In fact, the only enforcement mechanism we've had under the 2015 coal ash rule is what's called a citizen suit, meaning any citizen who feels that they are harmed by coal ash in a structure that's not in compliance could sue to try to have the courts force them to go into compliance. Now, there have been changes to the federal CCR rule along the line over the last 10 years. First, Congress acted in 2016 in response to the CCR rule that again started in 2015. Congress wrote a law that enables EPA enforcement, but that enforcement hasn't happened yet. Basically, this was a law that gave EPA the authority to oversee and enforce the coal ash rule, but it didn't require EPA to do so. And so far, EPA hasn't taken them up on it. In 2018, there were changes to the federal rule to extend deadlines and allow coal ash to go into ponds longer than would otherwise have been allowed. In 2024, there was a major revision of the rule, and this revision eliminated exemptions. This was important because as originally implemented in 2015, the rule actually exempted about half of the coal ash that's stored in the United States. For example, there was an exemption that said, well, if you stop putting coal ash into your pond before October of 2015, that pond is exempt from the rule. So those exemptions added up, like I said, to about half of the coal ash in the United States. In 2024, the revisions brought the majority of the coal ash into the regulation. In 2025, we've seen a proposal to extend deadlines again. So this would extend deadlines for those previously exempt units by an extra 2 to 3 years, allowing them to delay testing their groundwater. And testing the groundwater, again, is the initial step in moving toward any kind of cleanup or closure. In 2026, it's anticipated that there will be more changes to the rule, and they will likely weaken it. So let's move to state regulation in Indiana. Prior to 2015, Indiana had solid waste rules from the 1990s that applied to coal ash landfills and to the closure of coal ash ponds. So those solid waste rules applied to all kinds of landfills, and it included coal ash landfills. So we did have some regulation regarding testing groundwater and regarding how landfills closed. And then Indiana also had regulations about the closure of waste impoundments, and that did apply to the coal ash ponds, but only at the point where the pond was no longer receiving coal ash and it was going to close. In 2016, that same law that Congress passed enabling the EPA to enforce the coal ash rule also enabled states to have their own coal ash rules. Again, it didn't require them to do this. It just granted states the authority to write their own rule on coal ash, as long as that rule was at least as protective as the federal coal ash rule, and as long as EPA approved the state rule. And there are just a few states that have gone ahead with this so far. In 2021, the Indiana legislature got involved and passed the Indiana Senate Enrolled Act 271, and this was at the request of Indiana's utilities. Senate Enrolled Act 271 requires Indiana to write a state rule about coal ash and take advantage of that law that was passed by Congress. So the Indiana Department of Environmental Management, which is abbreviated IDEM, IDEM started writing the rule for coal ash. They put out their first draft of the rule. Indiana has a process for environmental rulemaking that involves putting out drafts more than once and then responding to public comments on those drafts. So they put out their first draft in December of 2022. So in January and February of 2023, the legislature responded with by adding provisions to Indiana House Enrolled Act 1623. This bill was already enormous, but they added a couple of pages about coal ash. And what they added basically said that IDEM was prohibited from including any provisions in our state coal ash rule that were not already in the federal coal ash rule. So basically, they didn't like the draft that IDEM had already written, and this blocked that draft and forced IDEM to go back to the drawing board and start over, basically writing Indiana's rule to be identical to what was in the federal rule. So in 2025, I should say in 2024, IDEM went ahead with a couple of rounds of drafts on their rule. They actually have to include some things that aren't in the federal rule because what they're doing is creating permits for coal ash disposal structures. That's what was allowed by Congress in 2016. The federal rule does not have anything about permits in it. So IDEM had to walk this balance between an Indiana law that says you can't have anything that's not in the federal rule and the requirement that they had to include permitting. Anyway, they've managed to walk that tightrope. And we are currently in the final public comment period. So they've released their final version. It is up for written public comment through November 26th. They just released it about a week or so ago. And then it will go to a hearing before the Indiana Environmental Rules Board on December 18th. Anyone with an interest in Indiana's coal ash can write a comment about the rule and turn it in by November 26th. I've included a link on how to do that here. And then at the hearing on December 18th, anyone with an interest in the rule can sign up to speak before the Indiana Environmental Rules Board. This final version, I've started reading the final version, but haven't finished yet. It's what you would anticipate. It has the permitting provisions that it has to have. And then other than that, it's exactly what's currently in the federal coal ash rule. And with that, I will stop and we'll see if there are any questions.
Thank you
Thanks.
very much, Indra. I beat you to it, Jill.
That's all right.
There is one question from one of our attendees. They were asking for, I guess this is really for any of you on the panel, but some of the health care outcomes. And so particularly, I would imagine for us in Indiana along the Ohio River, what are some of the health outcomes that we've seen associated with the coal ash ponds?
So I'd like to take that one on. The contaminants that are in coal ash include things that are toxic to the human nervous system, also things that are toxic to developing embryos, developmental toxins, as well as some contaminants that increase the risk of cancer, so carcinogens. We have, like I said, locations all over the state where coal ash has contaminated groundwater. In 4 locations that I know of, coal ash has contaminated private drinking water wells. And in all 4 of those locations, the utility has done the right thing and brought in replacement drinking water for those private wells. We know that the contaminants have the potential for health impacts. The problem is linking any individual person's health problems to coal ash exposure. The difficulty is that even if their private well had coal ash contaminants in it, all of us are exposed to neurotoxic or carcinogenic elements in a variety of ways in our lives. And so it's very hard to isolate where a particular cancer started or a particular neurologic problem started. So it's really difficult to point to any given set of patients and say, oh yeah, that was because of coal ash.
So Indra, just to follow up on that. So as we've seen, for example, with PFAS, you get kind of a clustering effect of these impacts that begin to add evidence for example, a class action suit or something. So do they have any kind of is the Indiana kind of Department of Public Health, or is there any kind of aggregation of, higher incidence of a particular cancer or impacts along the Ohio River, for example?
Well, so I would say that the Wabash River and the White River are at least as affected as the Ohio, just for starters. And then the area up around Lake Michigan is also, there's been a lot of impact to groundwater up there. Yeah, and you're right. With the PFAS chemicals, there have been some studies that were large enough that they could actually, run the statistics to prove association with exposure to the PFAS chemicals. We don't have the numbers that it would take to statistically prove that kind of thing with coal ash exposure.
That seems
least,
amazing, given the length of time that we've had problems with coal ash compared to even looking at some of the PFAS stuff.
Right. Yeah. No, for the most part, the contaminated groundwater is not being tapped for drinking water. I've mentioned that we've had 4 locations where it was discovered and then remedied, but yeah.
Indra, thank you so much for that. And just in the interest of time, making sure we have enough time for our 3rd presenter, and then we'll come back to all of you, because it seems like as I've been listening, I have a lot of crossover questions as you guys go through this stuff. So things about risk and about policy. So let's put some of those on hold if there's nothing else in the chat, Lynn, and welcome Maria to share her slides and hear this last piece of the puzzle, and then we'll come back together. Thank you, Indra.
Do you see my slides?
Not yet.
Not
And
yet.
Steve, nope. And Steve, I did want to acknowledge that I see your comment there in the questions, and I will get to that next session here.
Not yet.
Nope, not yet.
No, not yet. Okay, so we had them before.
I know we practiced ahead of time.
Yeah, we practiced. Yes. So
And here we are. There you go. Something's happening now.
And then, yeah, they will get them. We'll get them. Okay. Do you see them now?
I do. We're seeing your presenter mode with the the
Okay.
next
Okay.
slide on deck.
Yeah, I will change. I will change. Yes. Now?
Perfect. Yeah, that looks great. Thank
Okay.
you.
Yeah. So thank you very much for this invitation. And in the previous two presentations, we heard how damaging to the environment the deposits of coal ash could be. So wouldn't that be really nice to make something to turn this kind of waste material into something useful? So my role today is kind of show one way how we can perhaps utilize that. And I'm just going to talk about coal ash as potential source of rare earth elements. And so I was thinking that before I go into implication for recovery of rare earth elements, I'm just going to tell a little bit about what rare earth elements are, just for us to kind of remember, and also why they are important. So this is the a group of 15 elements here that we call lanthanides. And also we include under that category often scandium and yttrium, which are not really rare elements sensu stricto, but we include them in a group. We divide them into light rare earth elements and heavy. And this is an important division because there is different kind of demand and criticality of their use and for our economies. So these rare earth elements, they are used in almost every aspect of our current life. We use them in all the modern gadgets, in all the technologies, starting from clean coal technology, satellite communication, to electric cars, to medical device, to hard drives, and color TVs, and many, many others. So in the United States currently, 29% of rare earth elements are used for magnets, then as catalysts, polishers, in metallurgical field, batteries, glass, and others. So it's really difficult to imagine a kind of any technological advancement without access and availability of rare earth elements. So that's why for our country, it's so important to have this access to and availability so we can go ahead. So what's so magic about those rare earth elements? I just mentioned here only four major properties. One, that they have very unique magnetic behavior, and they really form very strong magnetic moment, and that's why they are kind of consistently magnetic and used in magnets. Then they have catalytic properties because of those, that's configuration of their physical configuration, but also they have high surface area and redox potential. Then they have great luminescent properties. They emit lights when stimulated by energy sources or electric fields, and each element they can emit different light. And also they have high melting points, which makes them really stable. So that's why they are just so critical in our modern technologies and in its development. This is a production of rare earth elements worldwide, and you've seen probably many similar diagrams before. Obviously, the red thing, that's production of China. So obviously, the production, the market, and the processing is so much dominated by rare earth elements. And yet we need them for almost any modern technological device. So that's a problem. We need to have access to them. And when we look at world reserves of rare earth elements in general, we estimated there are 120 million metric tons. Most of that is in China, Vietnam, Brazil, Russia, South Africa. We go down, down, down. And here, United States with with relatively small amount, at least as far as we know, of that resource. So what that means that either we have to rely on exports or on imports from other countries and mainly from China, or we have to look for some new sources that perhaps we can use for and try to recover those very precious elements. So where are those rare elements sit? So they occur in rocks. And main rocks are magmatic rocks, carbonatites, alkaline igneous rocks, peridotites, and yet in the United States, as I saw on the previous slide, we don't have that many of them. And those magmatic rocks, we call them traditional sources because that's from where most of the world mining of rare elements occur. In those resources, we have often up to several percent by weight of rare earth elements, which is a large concentration. That's what everybody would like to have. But unfortunately, in the States, we don't have that much of that type of resource. So as I say here, as conventional ore deposits become progressively depleted in response to large demand, the possibility of recovering rare earth elements from non-traditional, unconventional sources, such as sedimentary rocks or carbon-based materials, it becomes an exciting and yet a necessary direction. And coal ash is one of those non-traditional resources. So that's where, from now on, we'll be talking more about how can coal ash, what can coal ash do for us in that regard. Thinking about non-traditional sources, we have to remember that these are low-grade resources. Not comparing to several percent by weight in those big traditional resources, we usually have less than 1,000 ppm and often much less than 1,000 ppm of rare elements in those materials. Here is a diagram that I like to show because it shows a progression from coal reserves that we have plentiful in Indiana and still underground, through coal mining, and then through coal preparation that we have a clean coal that goes, or relatively clean coal that goes to customers, and we have a lot of reject. And then we go into power plants. And in power plants, when coal is burned, obviously at very high temperature, so all the mineral matter that sits in coal, it's melted. It's pretty much gets melted at that high temperature. And ash, that's where we get reject as a fly ash after coal combustion. So at each of these points, from coal in the ground to coal ash and acid mine drainage, we see there are rare elements recoveries opportunities. So the question is, how can we do that so that from this relatively damaging material, if it sits in its deposits, how can we turn that into really something that it's good for us, and it's good for Indiana, it's good for US economy and things like that. So a lot of work is being done in that regard, and Indiana government also just several months ago issued a executive order kind of to take initiative to work to look into those sources or resources of rare elements locally in Indiana. So just going back to coal ash, what is coal ash? It's a mineral matter from coal that is turned into this kind of melted, reworked temperature, kind of reworked material. So that's called ash. We already heard from previous presentations about coal ash composition, major components, silicates and aluminosilicates. And they usually, because they went through this high temperature, they form complex glass structure that it's as a result of this melting of mineral matter during combustion. And this glass structure is very difficult to leach. And it's kind of a paradox here that we talk so much about that how easy it can get into surface waters, into groundwaters, and elements can leach. When we try to leach that and extract elements from that, it's very hard. And we'll talk about more in a couple of minutes. So silicates and aluminosilicates that we have unburned carbon, that still there as a result of incomplete combustion. Usually it's not that much, a few to several %. And then we have crystalline phases like quartz still present or other minerals. And then we have trace elements. And trace elements such as we already heard, lots of arsenic that can leak. And there are some others, mercury and lead and antimony and cadmium. These elements that can do a lot of damage. Yet, when you, for example, arsenic alone, we need arsenic for various processes in our country. And what happens that actually we import quite a bit of arsenic. And we import this arsenic again. We import from China, we import from Peru. My goodness. If we could capture somehow some of these metals from that resource, wouldn't that be a really useful? That would be a game changer. And we have some other elements, and as rare elements are one of these. So I just wanted to show you some pictures. In my group, we've done a lot of work with looking at fly ash with microscopy. And so these are examples of organic particles. So we have some unburned carbon, we have some chars, isotropic chars, anisotropic chars. And then we have some spinel group and other minerals. And we have this glass that dominates, this aluminosilicate glass material that dominates the composition. Now, when we think about rare elements in coal ash, and I will show you on another slide how much we can expect, those rare earth elements are dispersed on nanoscale level. They are very dispersed, they are very small. And for example, here are transmission electron microscopy pictures that we have neodymium, we have cerium. They are dispersed as very, very tiny particles. And usually most of them are dispersed in this glassy association. They are dispersed throughout the glass. That's turned out so difficult to leach. And that's the main problem with extraction from ash. Some of them, they do occur in discrete minerals, and some these magnetic minerals that maybe we could pre-concentrate using magnetic techniques, but not that much. And some of that also sits kind of attached to unburned carbon, sits in organic matter and from original organic matter material. So in order to think how to really come up with optimal recovery strategy of those elements, we really need to understand very well their associations, how they sit in that coal ash. And then we can maybe design specific pre-treatment strategies, pre-concentrated strategies, and then use specific acids, then attract those various associations so that we can actually leach those and obtain high concentrates of rare earth elements. However, once, because the concentration is not so high, and also because they are so dispersed on this very fine scale, recovery from those low-grade materials is difficult and will be costly. As it was mentioned before, this is just a diagram that shows how much ash in the States we produce yearly. Obviously, the number, the volumes change. And you can see this blue area, that's how much is being utilized. So coal ash is beneficially reused to large extent these days in concrete and concrete products and for wearable. So, and this is kind of beneficial use. And obviously we want, instead of having that, put them on next to in a ditch, we really want to utilize them. And if we could add to that part that we already use for those specific applications, so if we could extract and utilize for rare elements, it would be great. And Indra already said we have a lot of coal ash and various deposits. That's pretty much the map that Indra shown in the previous presentations. And really we have in total probably more than 52 million metric tons in them. Most sit in deposits of Duke Energy. And there's a pretty big deposits that could be utilized. These numbers that we put here, area and volumes, Indra helped with those numbers, but also we went through all the closure reports trying to figure out how much ash sits there in. Now, thinking about rare earth elements, these are again 15 of elements that I mentioned on the first slide. Some of them are more useful and more so much more valuable than some other ones. And those in red, praseodymium, neodymium, terbium, and dysprosium, these are those that are most sought after. These are most valuable, and these are those that also at the highest risk for us of supply, because again, most of that comes from China. So when we look at a composition or concentration of those elements in ash, and here I just compare that to what we have typically in coal. So when we look at, for example, mineral matter in coal, let's say it's close to 10% of the whole coal by weight percent. So we already, because we know that most of rare elements are associated with inorganic matter and not with organic matter, we automatically expect concentrations of those elements in fly ash. And this is what we see. For example, for praseodymium, we have 36, 26 ppm in ash samples versus 3 ppm in coal. So really enrichment. Then neodymium, 140, 113 ppm versus 11 ppm in coal. A significant enrichment. So we have all that material that we have already automatically enriched concentration, but still it's enriched, but concentrations are still pretty low. We have to remember, it is low-grade material. And in addition to rare earth elements, also we have in coal ash, other elements that are of interest. And that's why we talk today more about kind of critical minerals, critical elements. And again, arsenic, gallium, germanium, lithium, nickel, vanadium, all of these, they are concentrated significantly compared to what we see in original coal ash. And these are also those elements that we really worry if they stay there, they are going to do harm. So can we really design, can we really try to make the process of recovery technologically viable and economically viable? This slide has a lot of numbers, but taking into account the volumes of coal ash that we have in Indiana, also the volumes of coal refuse that we have in Indiana, and taking into account the price of those elements, this is price in dollars per kilogram. I calculated how much value sits in those ash deposits that we have currently. So here is the number. I came to $5 billion US dollars that sits in rare earth elements in the deposits that we currently have. And as Indira said, in addition to those previous deposits that we have, every year we still produce about 5 million tons of coal ash in Indiana. So there is a value there that it's kind of it's captured in that deposit. Now, can we get it? Is there any way to get it? As I already mentioned, getting that is not going to be easy. I kind of put this slide as a roadmap to rare elements recovery. And this is a multi-stage process. It's a multi-stage process that requires a lot. It's very costly. Every step requires a lot of investment. So usually the process, because we start with a couple of 100 ppm or less than 1,000 ppm, we really need to upgrade. We really need to pre-concentrate to a couple of percent in order to take into the further steps of recovery. And pre-concentrating from 500 ppm to 2%, it's a very important and a very difficult task. And so the first step is usually physical beneficiation. So it could be various techniques could be used: sieving, magnetic separation, through flotation, density separation. Again, in order to be successful, we really need to understand where those REEs sit, what's their association. And then we could have either alkaline leaching or roasting pretreatment. Usually we go into roasting pretreatment, that we use both chemistry, chemical agents, plus high temperature, kind of to turn the material into a more leachable phase. And then we go through and then we go into very strong acid leaching. And usually we use, that requires a lot of acid. And it's like a lot of money would go into just those, this acid treatment. And then eventually, hopefully after this, we can go into relatively high concentration, and then we just go into purification. And then again, various techniques are being used. And also while doing that, if we also worry about, if we extract those elements, what's the rest? There is still going to be some residue. There is going to be some waste after that. So again, we need to look into those other beneficial uses, like aluminum recovery. We need aluminum. We import aluminum, or other applications. So again, it's technologically, we can do it. There are both lab studies as well as kind of pilot scale studies show we can do it, but it's a very complex and very expensive process. And
Maria, I'm sorry to interrupt. I just want to, I know you only have just a few more slides. I just want to keep us on time because people are going to want to ask you about a lot of this.
I just want it, just probably one last slide.
Okay, perfect. Thank you.
I might be very late. But, and if we do that, I just want to mention, we can have a lot of benefits. We can reclaim those areas. We reduce the volumes of that waste. But again, while doing that and going towards that, we need to also take into public perception in mind. So conclusions are obvious. We have a lot of coal. We have a lot of coal ash. And if we could turn that into beneficial use, that would be just great. However, it's a low-grade resource, so technologically possible, but in order to make it feasible economically, we have to have a major investments to come into in order to start that. And this is the end. So thank you very much. This is just how beautiful coal ash looks under microscope. Thank you.
Great. Gosh, so many things running through my head about that. I'm guessing other people may have questions as well. As you were talking, one quick thing, could you clear up for me? You're talking about those last steps. Do we have additional risks being introduced from this recovery process? Is there, you mentioned a lot of acid washing, a lot of things going on. Is the process of recovering present another set of risks associated with this?
There will be some, because probably there are some ways to reuse the acid and make it really not to be confined, So, but we will need a lot of. So even though I think that policy-wise, even though we have those regulations that Indra showed us regarding the storage. If we have a kind of mineral processing, we would have to have some additional rules introduced in order to make sure that everything is done safely and without harm for the environment. It depends, what, for example, when we talk about recovery of rare elements, in addition to ash, we also think about, for example, acid mine drainage. And so different scale of different type of waste we do expect. In addition, some based on pilot scale studies, they say the amount of this additional waste is not going to be that huge, and we can really not only handle that, maybe even turn into useful materials. So again, but we won't know precisely about until we have a facility that we have a real testing, and we know we have enough material to really come up with good statistically relevant amount of data in order to evaluate that. We are at this point, we just have some kind of efforts to see how it's going to work on lab scale or pilot scale, and we need more than that.
Yeah, sounds complex. Well, I know Lynn is going to probably also watch the chat. Looks like maybe we have a question in there. Do we, Lynn? If not,
yeah, we do have one from one of our scientists here at Purdue, David Warsinger. He was asking, I think this is for you, Maria, what water streams are available from the coal plants? And if these are considered for critical mineral recovery, are they more or less cost effective than processing the coal ash? And I know this is something that we're looking at here at Purdue, is how much is in the actual water.
Yeah, so when water, I probably would more think about acid mine drainage streams, and this is this contaminated water that we also remediate. But in those streams, rare earth elements are already in a liquid form. So they are already we already have some steps that we wouldn't have to, that we don't need to do with when we use other solid materials. But when we look at concentration of rare elements in those streams, they are low, So it's like it's on one hand, it's maybe easier to extract. On the other hand, the quantities are not necessarily there. But again, there are companies that are doing that for example, in West Virginia, on some other states, and we work with these companies in Indiana as well, and we really hope that we can bring them, and we can have a field scale kind of projects to actually try to do that. And by doing that, we can obviously clean the waters, because then we can collect not only rare earth elements, but other elements as they are associated with that. So again, a win-win situation, as long as we can really go through this first step and show, to demonstrate that the process works.
Yep. Interesting. It's nice to have such good questions sitting in the audience like that. I wanted to come back to something that kind of links what you were talking about with something Indra was talking about in terms of the permanence of disposal. So Indra, you said that permanent disposal was really needed because the stuff just didn't break down, right? And Maria's talking about the same thing, like, can you extract it and use it for something else? But she mentioned putting it into concrete products, which I've heard about before. Do you consider that a more permanent disposal? And if is that, I guess, a better policy is to start looking at permanently disposing of this stuff than some of these ideas about, potentially recovery of it. I guess I'd like you to compare and contrast that to other things, other environmental challenges where we think we need more permanent disposal versus maybe reuse or recovery is maybe the right word. Any thoughts on how this sort of sits with other environmental contaminants that way, Indra?
Yeah, well, first, the two best disposal solutions I know of for coal ash are using it in concrete or bricks, something that locks away the contaminants, as Grace talked about, or if it's got to be disposed of, a well-engineered landfill that has a liner under the ash and a cover over the ash, and that's located on high ground, where there isn't a flooding risk. When it comes to recovery, I mean, it'd be wonderful if some of this material could actually be useful. I think one of the problems, of course, is that the recovery process itself uses some fairly harsh materials, it sounds like, and that what you're recovering is a minority of the coal ash. So you're still going to have the majority of the material left over after you do the recovery. And we'd have to figure out, what happens still to that material.
Yeah.
Once you go through
Right.
the recovery.
Sure,
Yeah.
the volumes are striking to me. So, yeah. Marie, did you have something you wanted to add in response to Indra's comment about how much is recovered versus we're still going to be left with a
Yeah,
significant
I
amount of
mean,
material?
yeah, I mean, I would like this not to be, it would be great if we didn't have to store it. If we could really recover that and for beneficial use. And you already see that 70% of that is being recovered in the United States for concrete, and it's nicely worked there, even, giving good properties to concrete. Now, if we could recover rare earth elements and perhaps other elements such as gallium, for example, that I do know is quite a bit of that over there. And if we could recover and add to kind of help the US economy not to and take away this risk of not having availability for our development of technological, that would be a great usage, because that's one thing to worry about the deposits. But if we can get this benefit and we can get locally this recovery going, and not to be dependent on 70% of our consumption on China, that any day can dictate the supply. We really want to kind of not to be in such situations.
Sure. I'm going to cut you off there just for a second because we have a couple more related questions coming in for you on the chat. And I want to kind of also just go back to the larger risks at some point here. But two questions in the chat that I see. How many samples sites went into the REE data, the rare earth element data? If that's a quick answer you could give so we could move to the next one. Do you have a sense of that? How many samples or sites went into that?
Right. I mean, what I was showing you two recent samples that I collected. I mean, we know we have a lot of data on coal ashes from Illinois basin, and some, if not that many, from Indiana. but it's a kind of a similar range that we see. So we pretty much, in general, I would say we pretty much well understand what we can expect in terms of concentration as well as associations. We would love to have more data from Indiana itself, from specific deposits, but I had difficulty with getting access to the samples because companies were not so willing to give me the samples.
Right. Well, maybe the new executive order and the new commission will help encourage some of that. There is a question that maybe either you or Indra could also help answer in the chat. Please feel free to do that about if the fly ash is in concrete, how do you dispose of the contaminated concrete after its use? Or does that really truly trap it there? Or is there a risk to even that ultimately, Indra? Do you happen to know, or any of you actually?
Yeah, no, actually, Grace, maybe you've got a better handle on that.
Oh, okay, Grace.
Yeah.
Great.
I think the general thought is that when the fly ash is kind of locked up in that concrete, that you're not going to have much risk of exposure to it. I think so it's considered safe that way, but that's a great question about what do you do, years down the road when you're done with that concrete and you're disposing of it. And I don't know that that's really followed. And that's also something that I kind of worry about, that if you were to expose this concrete to lots of water, for instance, whether we would get any leaching over time. But overall, it's a much safer use for it to be locked.
I believe that it would have to be really in very strong environment in order to kind of leach them. So I think it's relatively safe, I would say, in normal conditions. Yeah.
Great. So I wanted to follow up quickly, Jill, just with Maria. Maria,
yes.
I think there are several scientists at Purdue who might want to be reaching out to you about your work in the rare earth elements, because this is definitely something that we're interested in. So just to let you know, you might get a few emails if is this an area that you're going to continue to do work in?
So we actually work a lot.
Go ahead.
Yeah, so we are working with Indiana government kind of to evaluate what we have in and kind of potential for recovery, including all the environmental and economic implications. And we are putting together a big report that probably should be available within next several weeks. So I'm the one who kind of, so it's a lot of information there. And I hope that it will be really useful as a first step, to look what we have and think how we can touch it, what we can do, what we need.
Great. We can push that out to all the participants. When that gets released, let us know, and we'll make sure that all of the folks on the call, if there's a public location for it, that would be great.
Great. Thanks. I wanted to go back. We have just a couple minutes left. And Grace, I did just want to follow up with one quick question for you. Given your perspective and other experience in other states and that sort of thing, are there risks that we're not thinking about that we haven't talked about today? And are there approaches that other states are taking that you're aware of that we should put into this conversation in any way?
And I think the risk that come to my mind is just thinking into the future and how we go about. A lot of areas now are closing impoundments, and thinking about the safeguards that we put in place for closing impoundments. If it's just kind of putting a layer on top and leaving it there, how are we going to make sure that that is something that's going to last 70 years, 100 years into the future? Especially with those kind of climate change impacts that we talked about and flooding risk.
Yeah. I know, Indra, that's a particular point of interest of yours, is that closure piece, and we're all watching a number of those. Indra, last thoughts from you on things like that, if the policy should be focused on closure as much as any of these other things, or where are your thoughts on policy at this point of actionable items we should be thinking about?
I think the most imminent need is to stop the groundwater contamination. And that's where the policy is focused. It's just taking a long time to get there. So stopping that groundwater contamination, and then if it's possible to mine the ash back out of closed structures, closed landfills, or closed impoundments, for use that's not environmentally damaging, I think that would be a good thing.
Okay, I have to, it looks like we're just at 1 o'clock, so I'm gonna wrap up here. You guys, thank you so much. What a bang up panel of experts on everything from risk to policy to recovery. We really appreciate your insights. I think we made it through the questions in the chat. Steve, I think your question was answered in the chat. I hope that was true. Again, our speakers that always join us for this always seem willing to answer any follow-up questions. So if there's anything else on your mind, please get back with us as organizers, and Lynn or I will make sure to funnel you the right information. And reminder, right, Indra, that there's a comment period open of interest to everybody. So we will make sure that that is available and promoted as well. So with that, I just want to thank everybody so much for caring about our water resources, participating in forums like this so that we can stay educated and try to solve these problems as a community from lots of different angles.
And I just
Thank
want
you.
to say thank you
Lynn.
also from Purdue. And also, I think all of us with White River and HEC, we are looking at data centers and water and energy needs for early in 2026. So keep your eyes open for those opportunities to further engage. I think there's several engagements with the topics surrounding data centers coming up soon. And have a great
Thanks,
holiday,
Lynn.
everyone. Thank you.
Thank you very
Thanks.
much.
Thank you.
Thank you.